Good morning, good afternoon, good evening, everyone. My name is Pearl Winchester. I'm originally from New Caledonia. I have been working, actually I can change this slide so you can see it. I have been working 14 years in the water department of the government of New Caledonia, and now I'm working for Inside New Caledonia, which is a member of the network GeoDevNC, which aims to get the private sector and public sector in GIS together. I am the animator of the community of Oceania Geospatial Water Resources Workgroup, along with Nicolas. And Nicolas, I'll let you introduce yourself, please.
Good morning, everyone. My name's Nick Metherall. I've been supporting this working group with Pearl this year and last year. My background, like many of you as well, is in hydrology, and I'm currently completing my PhD on environmental monitoring of catchments, river catchments, looking at surface water processes and groundwater processes. And yeah, today I'll share a little bit as well with Celine and Cyprian on this topic of flooding, but I'll pass back to Pearl to introduce the topic a bit more.
Yeah, no problem. So yes, welcome to this. It's our third technical webinar, and it's going to be on the floods, flood forecasting. And so today with us, we have Dr. Céline Catouin-Gilbert from the National Institute of Water and Atmospheric Research, New Zealand. So she's the leading hydrological scientist on flood forecasting at NIWA, and she's actively researching hydrometeorological ensembles forecasting systems, flood and inundations modeling, forecast communication, and end-user decision-making. Well, around flood, of course. With us, we also have Cyprien. Cyprien, if you could just put your camera 2 minutes so people can see you, please. Cyprien Bosrel is also from NIWA, New Zealand. He's a hydrodynamics modeler over there, and he's actually at the core of the development of some open source flood forecasting tools like BJ Floods. This tool is useful in predicting the impact of floods ahead of time, and we will talk about it along in the webinar. So a quick word on the community of Oceania Geospatial. I'll leave the floor to Nicolas, please.
Thank you, Pearl. So yeah, just a bit more information about this group for those of you who aren't aware of it. This is the Water Resources Working Group of the community that formed out of the Oceania Geospatial Symposium. And in essence, this group has a number of key themes and topics, including rainfall, surface water, and groundwater. And of course, this covers other areas such as the drought, water quality, ecosystem services. And the topic of today is more around flood hazards. And yeah, in essence, it's kind of this group kind of looks at the confluence between water resources management, the region of Oceania, as well as the skills associated with geospatial or geographic information systems and Earth observations. So that's a bit of this group in a nutshell. I'll pass back to Pearl.
Thanks. Yeah, you can actually join us on LinkedIn. It's the way we would like to interact, and that's where we actually put some information, tips, and best practices. We also share the slides and the replays from the other webinars, so don't hesitate to join us there. I'm actually going to leave the floor straight away to Céline, which is going to speak about, well, flood forecasting. Please,
Thank
Céline.
you, Pearl. I'm just going to share my screen.
Yeah, I'm going to stop mine up.
Can you now see it?
Yes, it's not the right one. Oh yeah, that's the one. It's good.
Okay, so yeah, and I can't quite see you anymore, but so I'll just put a timer. Cool. So thank you, everyone. So I'll just introduce myself in Te Reo. Tēnā koutou, tēnā koutou, tēnā koutou katoa. Ko Pyrenees te maunga, ko Garon te awa. No wiwi aho, ko Céline Catoen-Gilbert toko ingua. So my name is Céline Catoen-Gilbert. I'm originally from France, but I'm based in New Zealand in Christchurch. And today I will be sharing some of the perspectives on the research and work we've been doing in flood forecasting in Aotearoa, New Zealand. And Pearl asked me to kind of maybe reflect on what is the complexity of data and modeling that you have, and depending on this, what kind of flood forecasting you can have. And so I've tried to present the work thinking about that perspective, and then concluding with what are good practices maybe and key messages from our learnings to share with you all. And thank you, Pearl and Nick, for having me. So I'll first start with the valleys of depth concept of the warnings value chain. So some of you might be familiar with this, but basically flood forecasting science really kind of starts with observations if you have some, weather forecasting if you have any. You can get more complex and integrate with hazard forecasts, go all the way down to impact-based forecasting. And then having all that information connected together, often you have to communicate warnings, make decisions. And so as you can see, it's quite a complex chain of disciplines, of skills, of modeling, and it includes people, behavior, and it's not always simple and straightforward. And you can have very good forecasts and models, but you've got the wrong decision because you don't have a good integration and trust in your community to have the messaging go out, or the opposite, where you only have observations, you don't have necessarily good models, but they're good enough to help you, and then you can have a good decision and a good outcome. So it's important to really look at the whole chain when you look into flood forecasting. So in the context of New Zealand, it's an island in the Pacific, and it's got a very complex terrain where we've got the sea to mountains. So that means that we get extreme rainfall amounts up to 15 meters per year in the Southern Alps. We have, and then it can be really dry on the other side. And I know a lot of islands are kind of very similar in a way, where it might be different from the west and the east. We also have lots of short rivers and really fast rising rivers. So typical concentration time in New Zealand is less than 12 hours. And so that means that from a flood forecasting point of view, it's really challenging. You can't just rely on the data. You kind of have to use forecasts to have enough kind of warning. The other thing to know about New Zealand is that the responsibilities for flood warnings are the local authorities. So they're the ones, very local. We have 16 regions. They're the ones that issue the flood warnings. At national scale, we only have weather warnings. So we don't have a national agency in charge to coordinate flood warnings in New Zealand, or flood response even. So one thing is, if you don't have, huge amount of network of data to kind of find, what the rainfall's doing, what the flow's doing, you still can have a lot of data, historical data, local knowledge. So do you have photos of historic floods or information, and that can really help get an idea of, how to know the history of the place and what the floods can be like, and that can kind of inform, warnings in a way. Another one is indigenous knowledge. So in New Zealand, during Cyclone Gabrielle, Marae played a huge roles in sheltering people, in getting organized and passing information, and they can really they practice, and the behavior, the tikanga, can play a huge role in emergency management. It's not yet being leveraged as it should be, but there's a lot of knowledge there. Another key example is a couple of days ago, we were at Wairua in Little River. So the town's name in English is Little River, and in Te Reo Maori, it's Wairua, which means rising water. So they're different, but in the Maori, you've got the knowledge that this is a river that's going to rise, and it can rise really fast. And so there's always internationally, there's a lot of movement as well to look at how indigenous knowledge warning systems can kind of bring information and indicators of, what might be where you might see floods coming. And so that's something that is underexplored, but is starting to kind of looked at. So that's something, if you don't have any long-term data, you can still kind of leverage the knowledge, the local knowledge you have somewhere. Another point is, if you do have data, one key thing is getting data during a flood or before or just after is really essential. So we had some floods in New Zealand in Westport in July 2021. They were the worst since 1970. And something that we did is we had 3 gauges in the same location, and 2 of them went down during the flood. But we also were able to capture some flow rates just before the bridge closed. And that was the highest measurement ever in New Zealand, but that allowed to review the rating curves of the flow and really bring some huge information for modeling forward in afterwards, after the event. The other thing that was really crucial is we were able to send a team with the local West Coast Regional Council team to do post-event survey. And so the map that you see is the result of measuring the heights of the maximum flow depth around town, and that really constructed what we think is the best observed information of the impact of the flood. And what you can see is that the town is in the middle, and it becomes an island when it gets flooded like this, and and you can't evacuate past a certain point. So yeah, that's really critical to know when you're going to get flooded in this area. And so that map was a huge benefit for modeling and calibrating models afterward. And it was also reused when you had another flood later as a way of, okay, where do we need to evacuate first? And so, yeah, key message is it's really important to get the data when you can, when there's a flood, and be prepared for this. A key thing when you want to look further and you want to have rainfall forecasting in New Zealand, we found that because of the topography, because of the rainfall that we get, we really need high resolution convective scale weather models. So on the left is it's the total rainfall during a flood event in 2014, and on the left it's the catchment delineation, and the triangle are the amount of rainfall you're getting, and the grids are what you're seeing on the rainfall forecast. And so you can see with a large scale model, you're not capturing any of the huge amount of rainfall, but on the right with a high resolution model, you actually a bit more able to see more realistically what the rainfall is doing. You can still see that the rain can be a little bit outside of the catchment, and that can mean all the difference between actually predicting the flood or missing it. But the key point is, for islands such as New Zealand with high orography, we really need high resolution for weather forecasting. If you have core scale and you have observations of rainfall, you can still do things like bias corrections, but it means you need access to an archive of forecast and also access to long-term rainfall gauges, but you can still then use it this way. Another thing is beyond the rainfall forecast, you can look into hydrodynamical forecasting. So for example, that is integrating rainfall forecast with hydrological models. In New Zealand, we have a physically based model, and it's basically solving a water balance equation on sub-basins, and then it's using a routing scheme to kind of get the water traveling down the river network. And we're lucky in New Zealand that we have data, soil data for characterizing the soil depth, the kind of groundwater information, how it infiltrates, and that means that we can have a model that doesn't necessarily have to be calibrated, but can cover the whole country. And so this means we can then use it for doing river forecasting. One point, and that relates to the rainfall forecast maps that I showed, even if you have high resolution, you can still have the rainfall falling slightly outside of your boundary of your catchment, which means you miss the flood. So one key thing that is really useful is to actually have an ensemble. So that means you don't use one scenario of rainfall forecast, but a whole bunch of them. And that means that then it translates into getting discharge forecasts as an ensemble. And that is a very nice way of trying to capture the uncertainty that you might be getting from the weather forecast being slightly off spatially and temporarily, for example. And so this is an example of what happens. So this is the river buller, and on the left we have one high resolution weather model. That's computationally really intense, so we can't run many, but we can still perturb it statistically. So that means we're multiplying the rain up and down locally and spatially and temporally, and that kind of means we have a statistical ensemble. On the right, it's a real dynamical ensemble where we've run the models the weather model 18 times, so that's really computationally expensive. But you can see the main difference between the two is that with a real ensemble, you really have different scenarios where the timing of your peak can be a little bit more different. Whereas on the left, when it's just a perturbation, all the members are doing kind of the same trajectory and the same timing. It's just that it's a bit more or a bit less. And so it does show that real ensembles are a bit better at capturing the realistic uncertainty of what might be happening, a couple of days ahead, compared to the observation that are in red on the left and in black on the right. And so ideally, if you've got rainfall, trying to have an ensemble, whether it's by perturbing, having scenarios, or real ensembles if you can, but that can be quite expensive. Another thing that we've done in New Zealand is we went from catchment scale, where we're just predicting at one river location, to the whole country. And so we had the ingredients, as I said before, where we had a weather forecast, we had a national hydrological model, and we didn't have flow gauges everywhere, so we couldn't calibrate everywhere. So the approach that we used was to basically run long-term simulations with the model. And then every time we have a forecast, we can put our forecast relative to our simulations. And so we've basically turned our long-term simulations into categories of normal flow, really high flow, or very low flow. And then that allows us to basically give a forecast of where across the whole country we think the river are going to be. And so it's an experimental operational model, but here this is an example of a video showing an event. And so on the bottom right, it's the total accumulation of rainfall. So if you just look at the rainfall, you see the entire region of Canterbury being in the purple, so high rainfall. But it doesn't really tell you which river is being impacted. Whereas if you look at the river, you start seeing that it's only the foothill rivers that are going to extremely high, but the rivers with the headwaters on the Southern Alps are actually not as bad, and they're quite low. And that's because it was an atmospheric river that was coming from the east and got held up by the mountains. And so even if you can't accurately show the discharge forecast, this is a good screening tool that allows you to distinguish where it might get worse in the river by coupling your weather and your hydrological model. And also we've been producing information via social media and kind of explaining where things might be worse, and that's a nice way of raising awareness of what might be happening with flood forecast. And so that study, there's more details if you're interested, but it was really getting a scientific feasibility proof of concept, and we've done this. It was a huge amount of engaging with stakeholders, and that shaped really the co-design of how we built the system and tested it. The next step, so this is going back to a catchment, but it's the next step down the flood warning value chain, where we're integrating weather forecast, sea level forecast, and river forecast to actually look into more impact-based, where you're actually you're using a hydrodynamic model to see where is the flood depth and the flood extent for a flood event, for example. And so what we did for this project is we having all those boundary information, and then we did a library of hydrodynamic scenarios. So we took peak sea level, we took peak flow. All the dots on the right are 100 different scenarios of a combination of river level and sea boundary.
Yeah, we can't hear you.
Moment. Can you still see my screen, or do I need to share it again?
No, it's all good for the screen, and you're back on the microphone.
Okay, so cool. Sorry, my connection always does this at work. So basically, those scenarios were done offline, where you can take a long time with a hydrodynamic model to work out what is the flood extent and depth. And then in real time, what we do is we interpolate in between the scenarios, basically. And that allows to predict, 2 days ahead, what might be the maximum flood depth and flood extent. Another thing that we've done is we started looking at, can we do better by having hourly information? And so we started using, so this is ongoing work, where we started using machine learning so that it can, with the last 8 hours of forecast, river forecast, sea level forecast, you can start predicting what the map is doing. And so I think hopefully you see the movie, but it's really interesting because as you're progressing and you're seeing the ensemble diverging, and what you're seeing is basically the median of all the flood maps. But you can see how the tide is coming in and it's flooding a little bit and down, up and down, up and down. And it's really at a certain point, it goes over a threshold and then it starts flooding kind of everywhere. So this is really good if you have lots of information, lots of maps. At the moment, this method can't really generalize to any other places where you don't have that information, but it's kind of worth exploring more. But also from a emergency management point of view, it allows you to tell you when the peak is happening in the town and when to evacuate, for example. So it has that extra information that just interpolating between the maps we can't have. We just know the maximum over the period, but we don't know exactly when it's going to peak and when the water is going to recede, for example. And so all of what I've shown so far is on the physical science side of things, but we've done also some work in social science. We had 3 events in Westport in July, and what we've done is we did some interviews with participants that were quite different hats. So people that were making decisions, people that were providing information. And the aim, it was to understand what the emotional experience is of people involved in flood forecasting and response during flood emergency. And we were wanting to try and understand how, the forecast information that you might provide or the observation, how the emotions might maybe impact how you make decisions. And we actually were quite surprised to see that it can impact quite a lot. And so the people always had different hats. So some people were information provider at some point, but were also decision makers. And so, for example, they were technical advisors, liaising information between organizations, or they were planning evacuation or managing staff to organize the response, for example. And so some of the key quotes that we saw were as follows. So feeling positive and confident about the team providing hazard forecast information and interpretation, and that it is reaching the right people and informing key decisions as best as possible. Another one was when I went out to my car, I actually just broke down and had a really good old cry in the car. And that took me by surprise because I'd never felt like that before. It was a different feeling than anything I've ever had in my life. Feeling even more mentally and physically exhausted, feeling worried about getting it wrong. So it really gave us a picture how physically and mentally draining the response can be on making decisions. And so there's a report about it. It's really rich in information. But a key other thing is that there's a lot of cognitive biases that people can have. So I'll just give 2 examples. Availability bias means that you have a tendency to rely on information that comes readily to mind, memories or experience. So in the first flood event, when there was a massive, the whole town was flooded, people hadn't had an event like this before. So they even if the forecast was saying it was going to be very bad, they didn't think that would be the case. And so what came to mind was, oh, we don't need to evacuate. So they really waited until the last second to evacuate. 6 months later, there's another event. It turned out it wasn't as bad, but everyone wanted to evacuate the whole town 5 days before the event. And so again, because what was available to them was the last event. And so it's really important because it does show that your experience, your emotions, and your cognitive processes can really influence the behavior no matter what information forecast you're getting. The wishful thinking bias is another one where you have a tendency to not want to actually believe what might happen. Even if you believe the forecast, you're like, no, surely it's not going to be as bad. And we've definitely seen those biases in those interviews. And I think I'm getting close to the time. But basically, for an increasing complexity in data and modeling, there's a lot of things you can do. The first one is local and indigenous knowledge is always a great source of information to start with. Capturing data from flood events is key. It can really help increasing your modeling capabilities. Rainfall forecasting in Pacific Islands like New Zealand, you need high resolution to have a good job to be realistic. When you link into hydrological model, it gives you that extra information, but you need the availability of model. Always trying to have ensembles to capture uncertainty. And then you can go from catchment to national scale. And even if you don't have the flow gauges everywhere, you can use relative information to give an awareness. And then you can go all the way down with impact-based forecasting, but you need a lot of data and models to do this. And basically, my key message is even if you can have great models, social science is quite important, and understanding all of this and mandate and governance delineation as well is quite important. And I'll stop there. Thank you very much.
Thank you, Céline. It was it was very diverse and very interesting, actually. I learned a lot. We already have a question, but we will take all the questions at the end after Cyprien. I will let Nicolas be our second speaker, actually. Nicolas, the floor is yours.
Thank you, Pearl. And
citizen science for flood.
Thank you very much, Pearl. And thank you, Céline, for that. That was a really terrific presentation. And I'm sure there'll be lots of questions to come. I might even have to ask some questions in the email afterwards if we run out of time. But I'm just going to try to share my screen. I'm not sure if it's the presentation view yet. Not yet. Let me just fix that. Okay. I'm also having a bit of a slow internet connection, but it should work. Yep. Is that okay?
It is.
Okay, terrific. Yeah, so just kind of following on from Celine's presentation and bridging into Cyprien's presentation, I'm going to be talking a bit about how in these contexts where you might not have that kind of high resolution data sets, or access to really precise or accurate bathymetry data or elevation models, and or even just rainfall gauges and stream gauges, how you might try to fill some of the gaps through citizen science and participatory mapping, and how that might feed in as well into provide complementary data sets as inputs into some of these flood models and hazard maps. So I will just share a bit about this. Okay, so yeah, I think I kind of covered that. So I'm briefly going to cover around the hazard mapping around flood levels, a little bit about participatory water science and some experience from Water Watch, another organization that works in this space, and then a little bit about asset and exposure mapping. And that third point will probably be the main focus for this short presentation, and that will kind of bridge into Cyprien's presentation afterwards. So yeah, just in terms of the point I just made earlier, like you might not always have all of this these access to total stations and LiDAR and all of this equipment to be able to create these high resolution models. And so some examples of where we've had to work with communities to basically do participatory mapping and to kind of maybe do surveys to help fill in these gaps. This has involved working closely with communities and there's a range of different applications for collecting GPS data around flood extents around the flood levels at different points. And so some of this might involve working with community to look at water levels and around buildings and watermarks on buildings. It might involve going and marking out the extents on hand-drawn maps or using field apps. And I'll give some examples of that, but later on. But in essence, in the past, what we've tried to do is mark out these key points, and it just provides an additional line of evidence that supports some of this mapping. It's not quite as accurate and as precise some of the time, but it can provide a line of evidence when you have these big gaps in the data sets. I briefly wanted to touch on this idea of participatory water science and water watch. I think that this will be a topic that might come up in one of the subsequent, in one of the next webinars. But in essence, often during these flood events, you might have kind of a lot of disturbance of sediments and a lot of disturbance of various kinds of contaminants and pollutants that can be transported into waterways and across floodplains. And so having also this kind of raises a need to also have some forms of water and soil quality testing. And so one of the organizations that I've worked with in the past is called Water Watch, and we basically have these citizen science groups or community groups that will go out periodically and test water in various waterways and soils, and also, so that's for the chemistry side, but also for the biological or ecological side, looking at microinvertebrates, abundance and distribution, looking at other bioindicators, bird life, and other kinds of fauna and flora. So these can all become bioindicators that help shed light on water quality, but this will probably be covered in more depth in a future webinar. So yeah, I mean, in terms of water quality work that I've done in a flood context, I've done quite a lot of research on a particular catchment called the Bar River catchment in Fiji. I also did quite a lot of water quality research and ecological connectivity research on another catchment called the Magilla catchment in Northern Territory of Australia, which is downstream of the Ranger uranium mine. And so we were looking at a range of different contaminants such as magnesium sulfate and also radioactivity and heavy metals. And so being able to collect data periodically is really useful, but also working with local communities, Indigenous rangers, can help you to collect data more frequently and to have a better understanding of the temporal dynamics of water quality changes. Again, this will be covered in more depth in a future webinar. I think we'll have some people speaking about water quality. But in the paper that we did on water quality in the Bar River catchment, this kind of showed that there were some fluctuations, for example, in dissolved oxygen and pH, particularly in the floodplain, often around tributaries coming from the town with runoff and pollution, but also from in this case, the sugar mill was a source of variability in water quality. So this can be interpolated across your surface to kind of visualize those changes in water quality in this case. But a lot of the data that went into this visualization came from participatory mapping and citizen science. Now to come to the third topic, which will kind of bridge into Cyprian's topic, we'll talk a bit about this idea of the product of risk being kind of a function of your hazard area, your flood area, as well as the assets and the exposure of those assets to the flood area, and the elements of shielding and protection and that might be encompassed in vulnerability, and all of this kind of comes together to help us estimate total risk. But in terms of being able to gather all this data, it can be difficult for governments and regulatory bodies to be able to collect all this data. And so often we might rely on working with communities or working with wider participants to help us fill some of these data gaps. And so when we talk about collecting data around assets, I'm going to share a bit about a project called the PCRFI program, which was the Pacific Catastrophe Risk and Financing Initiative, and some of the survey data that was collected across the Pacific. And I believe that we may have some participants or audience members who are part of this project. I think maybe Emma Rosa from Samoa was a part of this project and helped collect some of this data. So this is one of the this is like an overview of the countries that were covered in the project and some of the number of buildings that were collected as data points in the project. But in essence, the context of this project was that there was a PCRFI 1 in 2012, working with NIWA, our colleagues from NIWA and GNS and others, to basically map out assets across the many Pacific countries. There was some modeling done to kind of model the distribution of these assets and exposure. Then there was the second PCRFI project, which worked across Cook Islands, Samoa, Solomon Islands, Tonga, and Vanuatu, and that was just over the last 2 years. And a lot of this data is then used to be inputted into or overlaid on top of the flood hazard maps, such as some of that could be potentially similar to what Selena's presented, those flood hazard maps and models, and similar to what Cyprian will present next around BG flood. A lot of these asset layers can be overlaid on top to help us estimate the total loss and damage or the replacement cost, and these kinds of that they can help inform policymakers and decision makers. The workflow that we used was collecting data through open source mobile applications such as Kobo Collect or QField. There's a range of other applications you could use in working with communities or working with governments, and working with citizens in citizen science programs or participatory mapping. The data is kind of collected in the field and then reviewed and cleaned and validated, and then it's put through additional processing that would then put it into these kind of riskscapes or BG flood or other on top of other hazard models, so that we can then estimate the risk or the loss and damage replacement costs. Yep, so these are some of the groups that we worked with in the ministries that we worked with in the various countries across Tonga, and I'm just trying to have the animation. Yeah, across Vanuatu and Solomon Islands, Samoa, and Cook Islands. So these were the survey teams. These were the people who were collecting the data using these mobile apps. And so they helped to design the survey forms. They helped to collect the data. And so a lot of these surveys were co-designed with the government and communities. And there was also some training and two-way learning on how to actually process the data afterwards. This was the training that was run that looked at various hazards, including tropical cyclones and sea level rise and flooding. And some of the data sets that came out of it, you can see each of these blue points in the Cook Islands was a building. And for each of those buildings, we collected a range of different data sets. I'll provide some more detail. I think we have some familiar faces here as well from Samoa. And a lot of the study was focused around Apia, but that also overlaps with the Vesingano catchment, which I know is a catchment that is quite prone to flooding. In Solomon Islands, there's a lot of peri-urban settlements, a lot of peri-urban expansion of informal settlements that are particularly vulnerable to flooding and landslides and tropical cyclones. So this was some of the sites that were surveyed in Solomon Islands. And then we have, so that was the total. in around Honiara and wider Solomons. In Vanuatu, there were quite a lot of points captured. And so for all of these points, there were about 32 different parameters or attributes that were collected for each building. They included the use of the building, the foundation, material, and type, the structure, the framing, whether it's a timber frame or concrete wall, the wall materials, the windows, the roof shape and pitch, the elevation of the height of the floor above the ground, and elevation above sea level, as well as the age of the building and the condition. And all of this information helps shed light on the potential exposure of these building assets to floods. So it helps us to understand not just what's on the hazard side, but also what's on the asset and exposure side. Yep, so this is Tonga. And this is an example of the kind of data that might come out. So you can see then the different classes of the building and the different material types you can symbolize with different colors. I'll give another example. I think that I'm not sure if it'll come up in, probably not, but I know that Cyprian has done a lot of work in Tonga as well. I'm not sure if that'll come up later, but we've also collected data on a range of different economic assets, infrastructure such as bridges, roads, airports, and different utilities, as well as other economic assets. And all of this data can feed into these kinds of exposure modeling, exposure models, including RiskScape, which has been developed between Catalyst and NIWA. And I believe that it might be relevant to the next presentation as well on BG flood. But this is just an example of where you overlay this is in Tonga, again, you overlay the asset data that's collected. You may symbolize the different building materials for different hazards, and then you can overlay the hazard map on top, and then you start to calculate the numbers of buildings and the total loss and damage. So this is just an example of how this data can be captured and feed into these flood hazard maps. And then information eventually can be disseminated back to the community as well. And so it's a full cycle often through citizen science and community participatory mapping to generate more complete data sets that inform these models and then you can disseminate the information back through billboards and other information products back to the community. Thank you.
Thank you, Nicolas. It was also a great presentation. Many topics also. I just wanted to have a small interaction time. And so I'm going to share this screen. Give me a minute. Up. So the people that are in the connected can actually give us their opinion on this question. Let me see. Is that the one? I gotta share it too, like this. Does it work? Yes, it does. So we have a question for you all. Do you know if in your country you have a GIS database where flood maximum levels are recorded? And actually, normally we do it with a special app in Teams, and I don't know why, and I'm sorry about it, but it's not working today. So if you could just please answer in the chat if you actually have an answer for your country. If there is a GIS database for flood maximum levels that are recorded. And I'm actually going to give my answer here.
if I may add a comment, Pearl, I think one of the questions is also, do you know of any of those databases, whether they are nationally held or if they are held by certain organization? I know, for example, from Nick's comment that I know SPC has a few of those databases because I did some survey myself.
Okay.
But I don't know where else would they be held. So that's an interesting kind of question to reflect on.
Well, you can actually write it down so we can think about it and talk about it after your presentation. Actually, if you can just write it down in the chat, I'll keep it for after your presentation. We might actually be able to talk about it a bit. So thank you, Emma Rosa, for Samoa. And thank you, Nicolas, also for Fiji. Thank you for New Zealand. And I think Cyprien is actually writing down the question. Anybody else wants to answer the question? If we have a GIS database for flood maximum levels that are recorded in their country? If not, when Cyprien is done writing his question, I will leave the floor to him. All right. Great.
All right.
Great question. Thanks. All right. And so I now leave the floor to Cyprien, which is also at NIWA from New Zealand. Cyprien, the floor is yours. I'm stopping wherever you are.
And I'll start my... There we go. Can you see my screen? Yes. Okay. Yes, I'm at NIWA in Christchurch, just a few doors from Celine, actually. So if I speak loud enough, she'll hear a nice echo of my talk. And it's kind of appropriate because a lot of what I'm going to talk about kind of echoes both Celine's and Nick's presentation. So I'm really glad that even though we only had a small chat about what we're going to present about, we are on the same page, and there's sufficient overlap to understand how things connect, but not too much. So I'm going to give a talk about open source tools that I was involved in creating in the last few years that are being used in flood inundation forecasting, a few of them around the Pacific. Now, I really like Celine's slide about the valley of death and the warning value chain, because I kind of tend to live on my little motu in the middle of the hazard forecasting side of things, and this is my narrow view from the island point of view of where I am, where you know, I kind of live in a world where I expect someone else to deal with predicting rainfall or river flow or wave height or storm surge or even some tsunamis, and I kind of try to think about what are the models that we can use to make flood maps, and and those flood maps, they obviously just a mean to an end. And whether I say a flood map, it's how many flood maps that we could produce, but they're really just a mean to an end, because like Celine showed, there's a real value in communicating what those flood maps really means, and how here, this is my very basic schematics of what you can do with those maps, but you know, it's part of a chain of a forecast system, and so obviously what I'm going to talk about is really just around those within that little motu, what we're trying to do, the motu of the hazard forecasting. Yeah, so when you have flood maps, to me, are a really strong mean to an end, because I guess I'm a very visual person, and I can communicate. I feel I understand maps a lot better than words, and they're a lot more meaningful to me. And I kind of maybe have this naive view that a lot of us behave that way. I know it's not true, but I think they're a very great tool for communicating about the hazard. I cannot think of if you really call an area and tell, oh yeah, this area around, I don't know if you think of somewhere like Loganville and you say, oh yeah, Pepsi is the area that is flooding, is at risk of flooding, we want to evacuate that. And that's kind of easy if you're local, but to me, I'm kind of like, oh, where is that? Why is this location so vulnerable? But when I see the map, I can, oh yeah, I can understand really quickly what that means. The flood maps to me also this seed to what we can use in something that does impact forecast, and that's what Nick was talking about. When you combine it with data like the Picography data set, then you can plug them into risk model like Riscape, and we do a lot of work around that, not necessarily within a forecast point of view, but within a risk assessment point of view. But they basically they're the same thing. You have your flood maps, you plug in some data that you have of people, where they are, where are their houses, what's the vulnerability of their houses or of the people, and then you get a bit of a better feel of what an upcoming event is looking like, whether it's going to do a lot of damage, how you can deal with your emergency management to better evacuate people or better help the people on the ground. And also at the forecast level is when your post-disaster management also starts. How much can we put a dollar value on what is about to be lost? And so, you know, then unlock fund to prepare the recovery and the disaster, the post-disaster event. How do you help people? How many people are going to lose their houses? How do you house them? So to me, the forecast map is a great tool to start for all this rest of the value chain. Now, a lot of the models that I use are physics-based model, and unfortunately, they're really too slow to run operationally. And there's what I call a the modeler's dilemma is that, well, if it's too slow, then you could just get a bigger computer. But it's the modeler's dilemma is that it's never worked in the last 40 years. We've always come to, well, if we had a bigger computer, then we could run this faster. But when we get a bigger computer, we want to run things at a higher resolution, which are much slower to run. And then that kind of leads to needing a bigger computer to try to run things operationally. And it's kind of this never-ending loop of we can run more physics, we can run more things if we have a bigger computer. So it's never really the end solution. But that doesn't mean you don't need a bigger computer. I think we all need a bigger computer. But the way that those forecasting system can ever work is by using those pre-computed scenarios. And that's what Celine touched on with her Buller example. I think the pre-computed scenarios means that you can then use either those scenarios directly, or you can try to interpolate between those scenarios. And there's lots of different things that can be used to do that. A lot more, and there's a lot of research going on into machine learning, into AI, and using what I tend to call meta models, which are models of models, to go from the pre-computed scenarios to a or multiple maps of your hazard. And that means you need a lot of scenarios, which kind of comes back to yeah, it's probably good to have that bigger computer because you're going to need to run a lot of scenarios beforehand before you have a system that you can rely on. And talking about bigger computers, one of the things that I've been working on for quite a while now is using GPUs to run physics-based simulation. So GPUs are these weird things that you have on the right-hand side of the screen, and they are graphic processing unit. So they are the graphic cards of computers. And because of gaming initially, these things were driven to do the math on a computer a bit differently than your normal processors. And because of that, they tend to be a little bit faster at doing the things that physics-based model wants to do. And on the left-hand side, we have a graph that's kind of complicated, but what this graph showed, and that's a paper we did with a colleague at NIWA, is we took a model that was quite well done, but worked on both the GPU and the CPU, and we could do some fair comparison of how much it takes, how much power it takes, how much time it takes to run. And what we showed was that, well, GPUs are more efficient in energy-wise. For the same amount of computing grunt or computing power, then the GPU will almost always faster. And this is not just on very strong hyper computing facilities or HPCs or supercomputers, if you want to call them like this. We showed that it was the case on supercomputers when we compared with very expensive, very fancy graphic cards, the thing that costs thousands of dollars. But we showed that it was also true for the GPUs that are coming with your laptop. Those brand new laptops that you get, slightly fancier than maybe the regular laptops, but those low-cost GPUs are the equivalent of a very good computer, consumer-based computer. Probably not as fast as what you could do on a supercomputer, but comparing with the cost, that it's not comparable. So really that focus is what drove the development of a model that we have that I've been working on for the past 7 years, called pgFlood. And it's a model that we wanted to be fast. We wanted it to be open source. We wanted to do a lot of different hazards that are related to inundation. So one of the first things that we decided early on was we couldn't really compromise too much with the physics that the model was capable of doing. So we're still doing something called the shallow water equation. And it's as simple as we can do with physics that still is realistic when we have shocks in the system. So we call it shock capturing. If you think of a dam break or a levee around the river that's breaching, or if you think of a tsunami propagating on a beach, these are really really similar to shocks. So where the water is flowing really fast, and when you have rebounding of the flow in a sense. Another thing that we were really keen on is, well, running on the GPU, but also not being too bothered with things that are like GUI, graphical user interface. Things that where you need to click a lot. We wanted to be able to automate things. So when we want to run 100 scenarios, then it's pretty trivial to make the model go and run 100 scenarios rather than having to click several thousand times. And also we wanted it to be open source. A lot of the logic of what we did with the development of the model is actually really linked to work we were doing in the Pacific. So these are some of the very early output we have from the models. When the model started working really well, we kind of went on and did some simulation of the 2012 flood in Nandi. That's the animation on the left, and that kind of was the first time that we used it in a real scenario that really mattered for people. And the other one was some work we did with the 2009 tsunami in Samoa and Tonga. And that's all the image on the right. And the model was really fast, and suddenly we decided, well, we're not running one scenario, we're running a lot of scenarios. And that's when we started really working with that. One of the things that, again, here, Samoa and looking at the 2009 tsunami, the logic of how we developed pgFlood was to be able to go at this cascade of scale when we are at the ocean basin scale on the left-hand side, all the way to really high resolution to look at the inundation. So if you look at the bottom right figure, I don't know if you see my cursor, but that's the southeast of Upolu here. That's where there was a lot of inundation. I mean, all along this coast, there was a lot of inundation from the 2009 event. And we really wanted to understand that. And to be able to understand that, you need to be able to jump across all these scales really seamlessly. The way that the model does that is using something we called an adaptive mesh. It's nothing new, but here we're using a slightly different one than most models because we wanted to still be able to run on the GPU really fast. And so we kind of use that design that's, we didn't invent that. That's from a few people who worked on GPU computation, kind of figured that's the best way to deal with it. So each of the squares are actually not a cell in the model, they are a group of cells in the model. And in this case, in the case below, they're 16 by 16 cells. So it's a block of cells. And then we can decide to split a block into 4 smaller blocks, which then we can refine into 4 smaller blocks, et cetera, et cetera. And that allows us to have really high resolution along the river, like in this example here of, that's the Waikanae River in New Zealand. So we can have really high resolution where we think the flood might happen, and that really matters, but places where we are pretty sure the flood is not going to happen, we're still going to simulate them, but we're going to simulate them at coarser resolution, and that allows the model to run a lot faster. And this has become really a key to this PG flood model. I have this cool animation of how the refining works internally in the model. So all these refinements is done by the model on its own. We just have to tell it where we think the flood might be happening, and the model kind of automatically goes from this coarse resolution to this fine resolution. On the top right, we have an example where we're following really the rivers and the drains, and you can see it can get really complex, but the input are relatively simple. And on the right-hand side, you have this example from Samoa, again, of the 2009 tsunami, where we had a really high focus on the southeast of Upolu, where we went from several hundred meters resolution offshore to less than 8 meters at the coast. Now, those models don't mean that we can bypass the hydrological model. I think all the models that Celine was presenting about, they're still very useful because they can be calibrated. They can be they deal with a lot of physical process that actually computationally would be prohibitive to try to deal with. So the groundwater interaction with the surface water, all these are really complicated, and they can be calibrated with hydrological models. So we see that the two models live together, and if you think of it in a kind of a maybe naive, maybe simplistic, simple way, is that on the floodplain where you're likely to have the inundation, then you really want to run a hydrodynamics model. But up in the hills where the water tends to stay in the gullies and in the river, then you probably don't need to. You can probably stick with a hydrological model. When we were and on the right, sorry, the picture on the right is what we're doing for a national scale flooding assessment that we're running. The green asher is where we run our hydrodynamics model, but the pink is where we still run the hydrological model. So we get flood maps where we have the green area, but we don't get flood maps for the other area. One of the things that I like to think that this picture on the top left is naive, where there's one river, one injection point, and one hydrodynamics model. When we look at it in reality, things get a bit more, a bit less what they look like. So for example, the injection point is not necessarily where on the edge of the model. So the edge of the model here is this, the black line. And also thinking of it as one river, one injection point, where it doesn't always work like this. The scenario in the south of New Zealand, where I think there's thousands or so injection point, and yes, they are towards the edge of the model, but it's not just one river, one injection point. Is we tend to inject all the little valleys on the side, and that's actually a challenge that we didn't foresee in the model. So we're working on some optimization around trying to make sure the model doesn't slow down when we inject a lot of rivers. Nick's presentation was really important in reminding us that, you know, the data collection part is not something that's replaced by the model. I think they live together. Post-disaster survey in particular, really useful for people like me who run models, because that's what grounds our results into reality. This is an example of GWR surveys and what the model did right after the event. So this is a model that we actually used around post-disaster and trying to think about what really happened, how much water was there, how can we explain what just happened. And we had model results, but it took us a little while until we get the results from the field survey to actually see that, hey, that model was actually quite useful. And well, not perfect. It was probably accurate enough to be able to make pretty useful decisions of it. The model is on GitHub, and you can find it there. I'll put the slide below at the end of my talk as well. It's always useful if you want to use it to refer to the releases, because as you can see on the top right corner, we always create different branch, and things get a bit complicated because we're still in active development, which I think is really awesome. We're not stuck behind something that we just like and don't like to change. We're just very flexible in what we're doing with the model. I'm almost done, but a couple of things that I wanted to highlight as well is a good DM when you're doing flood in a hydrodynamics model is really critical. In New Zealand, we kind of say, because we have a lot of LiDAR, we can afford to say, hey, look, we're not doing any hydrodynamics model if we don't have LiDAR. It's a bit harder to do that around the Pacific because there's only a few islands that have LiDARs, but more and more are getting LiDARs. And I think that's hopefully in a few years, we'll be able to have the same kind of policies around. If it's not LiDAR, we probably don't. We'll just wait for LiDARs to come to do hydrodynamics modeling. If you're looking for DEMs and you're interested in this kind of things, please look up the partner project. So this GeoFabrics, which kind of helps create DEMs, hydrologically conditioned DEMs for flood modeling. This was done across all the available LiDAR around the Pacific, and we created a 8 meter and I think a 4 meter DEM for that. So that should become available to any of you very soon. I thought maybe I would have time, but I don't have a lot of time. I thought I was going to talk a little bit about the logic of the machine learning, and maybe I can just go through that. Yeah, I'll go through that really quickly, but I think you already understand based on what Celine did. So I wasn't too sure how much Celine would go into this, but this is a machine learning kind of operation that is originally from a group of people I work a lot with in Spain. But the whole idea is to create a population of scenarios. Here, we went with 800,000. We went a little bit crazy, but because the code that we were using were allowing us to do that. But we couldn't run 800,000 scenarios. We decided to select 300 representative scenario, and that's a thing called the maximum dissimilarity algorithm. I don't think I will have time to show into that, but it's a really cool, neat algorithm. But once you compute your scenarios, then you can train your machine learning with the scenarios. And in a operational phase, you don't need to go through any of that. You just use your machine learning to get your results. And here we use something that's really, really simple called a radial basis function to do the interpolation between our scenario, really. And what this methodology does is kind of go back to a signal, whatever it is. Here it's meant to be a tsunami, turn it into parameterizing that signal, and that's in an AI system that's kind of done automatically by the AI, whereas in machine learning you kind of have to hold the hand of the analysis and be like, no, this is what predictors you get from this signal. So this is kind of the manual part, but it's very automatic how you go from your predictors to your flood maps. And this system, we found, and I think that's true for any of the machine learning or AI, is that you will find things that are a bit difficult and you have to go back to the training state and kind of modify things. One of the things that we discovered when we did this work on tsunamis that I'm presenting here is that if you think of the black line that I have on the screen as the topography or profile of the topography, and the blue line as the water level from different tsunamis, these are my different scenarios. So there's some are bigger, some are smaller. Now, if I look at it on the left-hand side, I can see that for this particular area, I know the water level, and I know the different water level for 1, 2, 3, 4, 5 scenarios. But if I'm on the right-hand side, I only know the water level for one event. The other one, I have to assume it because it just didn't reach. But for a machine learning algorithm, that's not very good information. Didn't reach. That doesn't mean anything. So you have to actually turn this into an information that works well for the AI or the machine learning. And most machine learning algorithm lack smooth solution. So we figured out that if we expand from what's the maximum value on land nearby that was reached, we got much better result than if we just told the machine learning algorithm, less than ground level or at ground level. That wasn't useful enough. But when we did that, suddenly our solution was a lot smoother and it was a lot more useful. The thing that we had to do out of that is that we just had to create a map that also included elevations that were below ground, but then we kind of removed that in a post-processing step. So all this method that I was talking about, it's been used in a couple of places, and the two ones that I've been heavily involved in was the SIFDIP forecast that's being run by Met Service, the Fiji Met Service. It's for the Coral Coast, and it kind of forecasts inundation, and it produces inundation map on the fly. It also produces those time graph at the top. And we have a very similar product that was deployed maybe a year or so ago in Samoa and in Tonga. And that one actually deals with a lot more multi-hazard. So there's rainfall, there's waves, there's a storm surge, all of this combined into different meta models that interact with each other. That's it from me. Here's a list of all the repository that I talked about. All of these are open source. There's a lot more out there, and we can discuss it if you want. But yeah, this is me. Thank you.
Yes, thank you, Cyprien, for this great work, actually. And the thing that everything is open source it's amazing, because it means that all the islands of the Pacific and actually everybody in the world can use it. So really, thank you for this, and thank you for sharing. Talking about sharing, I just wanted to have a quick word actually on the best practices from New Caledonia, because I thought they were also good to share. And as Cyprien and as Celine has been saying, and also Nicolas with the citizen science, is actually in New Caledonia, we have a maximum flood level measurement that is called the Caledomax, and it's a very, very simple tool that has been created. It's made out of just a piece of iron, actually steel, 2 fishing lines, some fishing buoys like floaters, and a piece of plastic, and they are encased in a Galva tube. And when the water is actually rising, it pushes the floater, and you keep the mark very easily, and you can actually get the data in a very safe way many days after the flood. We also have in New Caledonia some GIS standards for the flood maps, when we actually work with many different, what's the name in English, consulting firms to create the hydrological models and maps. And the last thing I wanted to talk about is actually we installed only a few years ago some flood ladders actually on the side of the road, just for the people in the car to see if the road is flooded, and to avoid well, it's for safety, it's for them to avoid crossing some flooded areas on the road. Thank you to the speakers, and we're actually going to switch to the question and answers. I know we have many questions. So let's switch to the questions and answer. I'm going to stop sharing my screen. Up. Where is it? It's here. And I know that actually the first question we had was from Jean from New Zealand, and it was a question for Celine about mathematics, actually. Oh. Have you seen that question?
No, I didn't. Where's that question?
So, the question is there a significant difference mathematically between forecasting urban and open space floods?
So in terms of the models that you use, yes, when you use urban models, it's a smaller scale, and often you want to take into account culverts and a lot of kind of small scale things. When we kind of doing larger scale, catchment scale, the processes that are involved are more things like infiltration, saturation at kind of a larger scale, and then you're basically traveling the water kind of on a more big scale kind of assumptions. And so, yeah, the models are typically quite different when you're looking at urban versus kind of catchment area and discharge. And also some models for urban are more using what you call hydraulic models. And so they're a bit more not 1D, but kind of 2D, where you're also looking at what might be happening in terms of where the water is going. Whereas for the catchment scale, it's often 1D, where you're kind of looking at the river levels. but you're not really looking at how the water might travel if it goes over bank, for example. And so this is where you have models like what Cyprian presented, like BJ flood, and this is where, you know, at least 2D and solving hydrodynamics equations. So the equations within the models are different because you're trying to solve processes at kind of slightly different scales, if that answers the question, hopefully.
Wow. Actually, you know what? I forgot something. Where is it? How do I do this? I'm actually supposed to give the microphone to everybody. Sorry about that. Where is it? Oh. Tac, paramètres. Is it here? I think it's here. Da-da. No, it's not here. No. I don't remember how we do it. They changed teams. I'm sorry, they changed teams and
I guess will you do this? There was another question from Jane, which I thought you were going to mention, which was
yes.
about, do the flood forecast models affect local governing bodies' evacuation plans? And then there's another one. So, and my quick answer was yes, via formal and informal relationships. And so NIWA with the West Coast Regional Councils, we've been working on various stages of model development over many years. And it's also one key message I forgot to mention is that to get to model complexity, you can start with very basic and then you can really build on it over the years and get more and more kind of complex. And this is exactly what happened with Westport, where we had a small and violent grant that allowed us to build a very basic flood forecast model in the Buller, and that was already in place before the July 2021 event. And via kind of informal relationship, because we knew people, they reached out to us and we ended up actually giving them a river flow forecast for the response. And then there was another event, and building on this, we had developed research models with more convective ensembles. And we also used this for the February event in 2022, so that was 6 months later. And in that case, so this is where it's interesting, where you see that the integration of disciplines is really needed, because the meteorology was showing the event was same or worse than the July event, because there was a massive atmospheric river, similar amount of rainfall you were expecting, but it was summer, and for the hydrology, it was dry, and the flood forecast, when you include the river, it was showing it was a tiny little mini-annual flood, so nothing to kind of panic. But because we have the way we are in New Zealand, where you have the weather warnings, and if you just look at the meteorology, we had a red warning, and the local authorities were thinking we need to evacuate the whole town 5 days before the event, and that was because, you know, they had experienced that July even before. But the river forecast, looking at them, it basically was showing you can wait, hold on, because it doesn't look like it's as bad. And I think via this information, it really kind of, you know, I think we had defense coming, like the whole town was really ready, but we were holding off, no need to evacuate, no need to evacuate. I think there was some a small evacuation, but the forecast was showing it wasn't going to be a big deal there. And then the opposite, the following week, our forecast, a tiny amount of rainfall, and because it was so saturated, the forecast was showing there was a chance for rural flood, and rural flood did occur. But it's something that if you just look at the meteorology, you wouldn't have captured the local impact. But other than this, because NIWA isn't mandated nationally, it means that, you know, it's only on people that you have informal relationship that request advice and information that this has occurred, basically. And that's basically answering the question number 2, which was, is there a system of coordinated forecast, risk assessments, and evacuation plans and implementation of the plans? It's very ad hoc. It will depend on the relations between the organizations at national scale and the local organizations, and then the system in place. And it's because we don't have like a national body in charge of doing this in New Zealand. So yeah, no matter how complicated you can be with your data and your models, if you don't have the right governance, it can still impede the response. Hopefully that answers Jin's question.
Yeah, Jean, does that answer your question? You should be able to talk now through the microphone, I think.
Yes, thanks, Lynn. Answered perfectly well for both the questions.
All right, thanks. And actually, a good transition with the other question from Cypria, actually, saying of the question was, can you think of where some of that GIS data could be held in the country? Like, actually, which body in every country should be the one kind of recording the maximum flood levels, and who should be the one having the flood forecasting map? And so this is actually something we can share. I can start with New Caledonia. New Caledonia is actually pretty easy because it's the government of New Caledonia which started creating the database for the maximum flood levels, and so it's centralized over there, and they're actually the one doing the surveys after the floods. Sometimes there's a mix with the provinces, but mainly it's working, and it's the same for the flood maps. The flood maps used to be co-constructed, co-built between the provinces and the government of New Caledonia, but it has been clarified very early in the system that the validation and the broadcasting of the flood maps will be done by the government of New Caledonia for the whole country.
Maybe if I can jump in as well and talk a little bit about some of the experience that I have, and maybe that some other people might join in, because I think overall me talking about the data in the Pacific is probably not the most appropriate thing. But I guess in my experience, what's happened is that organization like SPC have access to funding to go and do some surveys when there's a disaster. I know it happened with me in a few locations while I was working at SPC, and this data is always handed over back to the country. Sometimes, but SPC also keeps a copy internally so that to save for safekeeping, but also kind of acknowledge that the data belongs to the country. But also often we think about the country scale, but it's also at the local scale. And my experience working with Fiji is that this information actually belongs to the communities, and they are the sort of the custodian of that. And I think this is really great. On one hand, it creates for people like me who gets a lot of the work I do is consulting with the countries on what the flood map could be or how to create flood models, and I need access to this data. But that requires more effort for me to go to the communities to go get that data. But I think also it forced this links to happen between the people who might be doing some high-end modeling with the traditional owner of the land, who actually have a traditional knowledge about this. And it's not just about the last big event. It's about, oh yes, we build a village here because this area has a special meaning, or we have stories around flooding around there. So I think the indigenous knowledge, those traditional knowledge system that exist around the Pacific are really, really important. And we need to be careful that having a nice centralized system is good, but it also it's hard to make it work with this traditional knowledge. And in a system where the knowledge is held by the communities, it forces people like me, who might be just flying in the country with my big computer, to actually have conversation with the communities. Which, if that doesn't exist, if the information's too easily available, I might forget that and skip on that. So I don't know, maybe that will get people to think about that.
Thank you, Cypria. Does anybody else want to actually share its experience on this topic? No. All right. I had a question for Nicolas, actually, about the survey in Tonga for the buildings. You went quickly on it, and I was actually wondering how long it took to get the survey done, if you actually know.
So my understanding was that they took about, because I wasn't involved in that particular survey, I was involved in Vanuatu, but for Tonga it was about, I think it was about 2 weeks for the for Nuku'alofa, just around the capital, and then they did smaller surveys on the outer islands. So I think that would have been 1 week in each of the outer islands, but it was done. They broke up into small teams and they divided it up and they did one each. So I think altogether it was 2 weeks for the capital and then 1 week for the outer islands. But it didn't, they didn't cover every single building across the entire islands. It was more the areas of highest density for exposure. So like where the most assets were concentrated.
Okay, all right. Thanks, Nick. And what about Vanuatu then? Because you were in Vanuatu, you said.
Yeah, Vanuatu, it took us like it took up overall, if you added it all up, because it wasn't all done in one stretch, it was broken up. So, but I think in terms of the number, it would have been like 6 weeks or maybe 7 weeks, because they took a long time to do Port Vila and they did a lot of it, and they worked with the University of the South Pacific students. They brought a lot of students in, and so that was a good example of more citizen science. And then reaching some of the outer islands, I think was about 2 weeks on each. So yeah, it was about 6 to 8 weeks.
Yeah, it's shorter than what I thought, so it's good. Yeah.
Again, it's not covering all of the buildings everywhere. It's just the main economic centers. But I think in Vanuatu, it's usually, they're more concentrated, and then you have small settlements in the outskirts. So it's that's basically from our experience, that was what we found.
That's good. No, that's good. Thanks, Nick. Any more questions in the audience on anything else? Well, if there's no question, I'm going to share my screen again up to actually invite you for our next webinar that will be on water quality, and it's actually scheduled for October 3rd, and it still will be at 9 a.m. Fiji time. So I will share the link straight away on the chat, and I'm gonna finish with if you can all just put your camera on, because I would like to take a screenshot of all of us, because it's always amazing to see everybody coming from so many countries being together to talk actually today for the belt floods. So yeah, if you could just please turn on your screen. I'm going to share the link in the meantime. Like, all right. All right. There we are. I'm going to take the screenshot. Are you ready? 1, 2, and 3. All right. Did it work? Let me see. I'm going to paste it. I hope it works straight away. Ah, new people. Ah, I'm going to make a new one then. Up. Let's do it again. Ah, so many people. That's okay, Chris. Thank you for saying. All right, I'm going to take another one. You ready? 1, 2, 3. That's it. I think it's working. All right. Yeah, it is working. Perfect. Merci beaucoup. Thank you very much to everybody. Thank you, Nicolas, to be the animator with me of this work group. And I'll be glad to share the slides and the replay on the LinkedIn and also by email to the people that registered. And we'll see you next time, October 3rd, for water quality. If you have any questions in the meantime, if you have other subjects that you would like to be discussed, then just the same, interact on LinkedIn, tell us what you would like, and we will try to organize it for you. Merci beaucoup, Boula. Thank you very much. Thank you. And we'll see you next time.
Thank you.
Thank you all.
Céline.
Thank you.
Thank you.
And thank you, Cyprien and Nicolas.
Thank you.